Okay, so I guess everyone's cool. So we're gonna do, we'll start the topic for tonight, and it is called Taylor series. Okay, Taylor series. Okay, this is named after a famous mathematician whose last name is Taylor. Okay, all right. So let's just recall from last class a power series expansion. So let's just recall that if f of x has a power series expansion, it's a power series expansion centered at x equals a, it is of the form okay, so it just looks like this. I'm going to call this equation 1 because we're going to reference it a few times. So just f of x, this is the infinite series from n equals 0 to infinity. We have this coefficient cn, and that's multiplied by x minus a to the nth power. All right, so this was from last class. This is just a power series centered at x equals a. And we just give it a name. We're going to call it f of x. All right. So I hope that is familiar from last Wednesday. Okay, so what's cool about this is that we can actually, we can get an explicit formula for these coefficients Cn. All right, so that's what we're going to do right now. So let me just write that we are interested. And they actually have a pretty nice formula. So we're interested in computing the coefficients C sub I explicitly. All right. So that's what we'll set out to do right now. So we're going to try and get a nice explicit formula for the CNs or the CIs. Okay, these what I have highlighted here in the power series. All right. So it's not obvious what to do, but just kind of bear with me here. What if, so the first thing we want to do, let's plug in x equals a into equation 1. Let's just do that. So here's equation 1. It's right here on the top of my notes. And let me just plug in x equals a into both sides. So this gives the following. F of a, plugged in x equals a into the left side. That's fine. This will be c sub 0 plus c1 multiplied by a minus a plus c2 multiplied by a minus a squared, and so on forever. Okay, and I hope you guys agree that every summand except c sub 0 vanishes. So this is just c sub 0. Okay, because you're going to have a minus a in parentheses for the remaining terms. So everything I'm highlighting in yellow vanishes. Okay. So, all right, so we actually figured out the first coefficient already. So thus, C naught or C sub 0, we have a formula. It is f of a. Awesome. Awesome. So how about finding C1? So how do we do this? Well, let's try differentiating equation 1 term by term and see what happens. So let's, so differentiating equation 1, so 1 in parentheses, term by term gives the following. Okay, so we get a new equation, which I'm going to call 2. This will be oh, not equals. So 2. So I'm just going to take the derivative of both sides of equation 1. So I get f prime of x. Okay, that's the left side. And now let me differentiate the right side term by term. I get c1 plus 2c2 x minus a to the first power plus 3c3 x minus a to the second power and plus dot dot dot. All right, so I hope everyone can see how I got this. I just used the power rule on each summand of that power series, okay? And C naught disappears because it's a constant, and the derivative of a constant is 0. All right, so I hope you're all with me. And now let's plug in x equals a into this guy. All right, what does that give us? Well, I hope you guys agree, that gives us that f prime of a is just equal to c1. And why is that? Because every summand except c1 has an a minus a in it, which makes them 0. So everything I'm highlighting here vanishes. All right. So there we go. So we have our formula. So now we have an explicit formula for c1. It's just f prime of a. So let's keep going. So now let me differentiate equation 2. So we're just trying to get a formula for the coefficients c sub n. All right. So differentiating 2 term by term. That will give, okay, so on the left side, I get f double prime of x, okay? That's the second derivative on the left side. And now the right side, just use the power rule again. So we get 2c2 plus 3 times 2 c3 x minus a plus 4 times 3 c4 x minus a squared plus dot dot dot. All right. So I'm just using the power rule on each term. And now, yeah.
Never mind. You just swapped the order of the 3 and the 2 on your second term, so never mind.
Correct. Yeah, exactly. And now let me plug in at x equals a again. This will give us that f double prime of a is equal to 2c2. Okay. So I hope that's clear because the rest of the summands vanish again. So all these yellow guys vanish. And now let me just algebraically solve this for C2. C2 is equal to f double prime of a over 2. Yes. So we have a formula for C2. Let's do this one more time and see if we can somehow pick out a general form. So remember when we were trying to
seeing factorials.
Yeah, so factorials are gonna come into play. Yeah. So we're gonna try and trying to see if a pattern emerges and find an explicit formula for C sub I. So let's do this one more time. So I'm gonna call this guy 3. So differentiating 3. I'm just doing the same thing. Differentiating 3 term by term. That will give the following. So f triple prime, the third derivative of f, that's equal to 3 times 2c3 plus 4 times 3 times 2c4 x minus a. So I'm just using the power rule, plus 5 times 4 times 3 c5 x minus a squared plus dot 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 forever. Good. Now let's plug in x equals a. So f triple prime of A, that's nothing other than 3 times 2 C3. Okay, for the reasons as above, every summand vanishes. And now let me just solve this guy for C3. C3 will equal f triple prime of A over 3 factorial. Okay. So let's finally get some explicit formula. So more generally, we observe that the nth coefficient, C sub n, is. So does anyone know the general form? Does anyone see it? So if you look at C3, it should be a nice hint as to what Cn should be.
I think it's Ci or Cn is f. I don't know how to say this. F prime times the number of
So
f.
derivative,
F,
the nth
yeah,
derivative.
derived, differentiated however many differentiated n times. I don't know if there's like if there's even symbols for that.
There is, okay.
Over the factorial of n.
Yes, correct. So it's going to be the nth derivative of f, which we denote as f with a superscript, and the n is in parentheses of a. So this is the nth derivative of f divided by n factorial. All right, so that superscript parentheses n, that means the nth derivative of f, okay? So it's the nth derivative of f evaluated at a divided by n factorial. So that's our formula. So all along, these coefficients Cn actually had this formula, okay? So that's that. So since we have our Cn's, we actually can write our power series into a slightly different form. So thus, f of x, which we originally, so I'm going to write out our first expression for it. It was just C sub n multiplied by x minus a to the n. This is actually the same as, so I'm going to put our formula for Cn in for Cn, okay? So this is actually the same as the nth derivative of f evaluated at a divided by n factorial, so that's Cn, multiplied by x minus a to the nth power. Okay, so I just replaced Cn in the infinite series with our derived formula for Cn. That's all I did. So we have a new formula for a power series, okay? Okay, so this leads to the following definition, okay? Okay, so definition, DEF for short. All right, here we go. If f of x has derivatives of all orders at x equals a, then the Taylor series. So that's what we're defining, so I'm going to underline it. Then the Taylor series for f of x at x equals a is, it's just that series that I wrote above on the last equal sign. So it's defined to be the series of the nth derivative of f evaluated at a divided by n factorial multiplied by x minus a to the nth power.
And that won't ever diverge, right? Because
No, that will diverge mostly.
oh,
Yeah. We're going to look at the interval of convergence for this later. And it's going to depend what f is, what function we're taking the derivative of here. All right, so let me just write the first few terms of this guy. So this is, so I'm just write out the first few terms. This is f of a, that's when n equals 0, plus f prime of a multiplied by x minus a, plus f double prime of a over 2 times x minus a squared, and then plus dot, dot, dot. All right, so I just wrote out the first 3 terms without the sigma notation. Okay. All right, so that is the definition for a Taylor series at x equals a. And we just have a special piece of terminology when the Taylor series is centered at x equals 0. Okay, so actually Tommy last class alluded to this. That's a Maclaurin series. All right, so let me just write that down. So the Taylor series, for f of x at the special value x equals 0, okay? So it's a specific case of a Taylor series, is called the Maclaurin series for f of x, okay? I'm not sure why we give the series centered at x equals 0 a different name. That's just historically what it's called. Right? So it's nothing other than the above definition with x being precisely 0. That's what a Maclaurin series is. Okay. So I hope everyone's with me. Just let me know if anyone is, just let me know if you have any questions. All right, so we also give the nth partial sum of a Taylor series a special name, okay? And these actually turn out to be really important in real world applications, which I'll explain a little bit later. So, so I'm going to define the nth partial sum of the Taylor series. So it has a special name, all right? So the nth partial sum of the Taylor series for f of x, which is usually denoted by p sub n of x, is called, so we're just attaching a piece of terminology to the nth partial sum, is called the nth Taylor polynomial for f of x. All right. So the word here that I'm defining is nth Taylor polynomial. All right, so we're just giving a piece of terminology, a special name for the nth partial sum of the Taylor series. All right. So let me just list out the first few of these Taylor polynomials. So let's just look at p sub 0. So the zeroth Taylor polynomial, that's just going to be f of a. Okay, it's the first term in the sequence. P1. So I'm summing from n equals 0 to 1. It's going to be the sum of the first 2 terms. So it's going to be the nth derivative divided by n factorial, x minus a to the n. So I'm just going to do the sum of the first two terms. That's f of a plus f prime of a multiplied by x minus a. Okay, so that's the first Taylor polynomial. And let's just look at p sub 2, the second one. So that's just going to be f of a plus f prime of a multiplied by x minus a, and then plus the third guy. The third term is going to be f double prime of a over 2 multiplied by x minus a squared. Okay. So those are the first three Taylor polynomials, okay? And I'll show you guys later why we care about the Taylor polynomials, but essentially these Taylor polynomials provide really good approximations to our function near the point x equals a. So if you look at the graph of like the second Taylor polynomial and the graph of the function f, you're going to see that the second Taylor polynomial will look really similar to the graph of f around the point x equals a. So it's a local approximation. It's not a global approximation, it's a local thing. All right, so I'm going to show you guys that later with a nice interactive thing. All right, so that's kind of cool. Okay, so that's that. So for the Taylor polynomials, we also have the corresponding statement when it's centered at x equals 0. Those are called the Maclaurin polynomials. All right, so the nth Taylor polynomial for f at the special point x equals 0, so that's Maclaurin, is called, as one could guess, is called the nth Maclaurin polynomial. The nth Maclaurin polynomial for f. All right, so same definition as before, but the a value is precisely 0. Okay. All right, so we just give this special name for when the Taylor series is centered at 0, and that's Maclaurin. All right. All right, so let's do an example. Let's actually compute some Taylor polynomials, okay? So this will be nice. So let's find the Taylor polynomials. So example, find the Taylor polynomials. So let's find P0, P1, P2, and P3 for the function f of x equals natural log of x. And I need to tell you centered at which point, and it will be at x equals 1. Okay, so this is all of the data that you need to find Taylor polynomials. You need the function and you need the value that we're centering our power series at. Okay. All right, so for the Taylor polynomials, really the only thing we need to figure out are the derivatives evaluated at our center point. Okay, so we really just so we need f, the nth derivative of f evaluated at 1, 4, n equaling 0, 1, 2, and 3. Because that's what the definition calls for. We need those nth derivatives evaluated at x equals 1. So let's just work that out. So let's look at the 0th derivative. So the 0th derivative is just the function itself. So we have f of x equals natural log of x, and let's plug in 1. So f of 1 will be 0. Okay, because natural log of 1 is 0. Now let's look at f prime. F prime of x is 1 over x. That's the derivative of natural log. And now let me just plug in 1. So f prime of 1 is nothing other than 1. Very good. Let's just do this 2 more times. So let's look at f double prime of x. So what's the derivative of 1 over x? It is, you can use the power rule, it's negative 1 over x squared. And if we plug in x equals 1 into this guy, you will get negative 1. And we just need to do the third derivative. So
I think you forgot a prime over.
Yes, I did. Thank you. Yes. And let's look at the third derivative, f triple prime. Take the derivative of negative 1 over x squared. Just use the power rule again. That will be positive 2 over x cubed. And evaluating that at x equals 1 will give you positive 2. Okay? All right, good. So now let's plug this into our Taylor polynomial formula. So P naught, that is always just f of a, where a is the value that you're centering your power series about. So that's just going to be f of 1, which we figured out to be 0. So that's P0, P1. So P1 is going to be f of 1 plus f prime of 1 multiplied by x minus 1. Okay, so that's just the first partial sum of our Taylor series. And let's just plug everything in. This will just be x minus 1. And why is that? Well, f of 1 is 0, so that goes away. And f prime of 1 is 1. Okay, that's why I'm just left with x minus 1. Very good. So now let's figure out P2. So P2, so I'm just going to write it in the expanded form again. P2 is f of 1 plus f prime of 1 multiplied by x minus 1 plus f double prime of 1 over 2 times x minus 1 squared. Okay, so that's the second partial sum of our Taylor series. And this just turns out to be x minus 1 minus 1/2 times x minus 1 squared. Okay. So I hope you see that, because f double prime of 1 is negative 1. So that's why it's minus 1 over 2. Good, and then P3, I'm just going to write the final answer for it, but check this. P3 will be x minus 1 minus 1 over 2 x minus 1 squared plus 1 over 3 x minus 1 cubed. All right, and just check this, please. Okay. So these are the first 4 Taylor polynomials. And what's cool about them is that as n gets larger, so as you look at P3, P4, P5, the graph starts to look more similar and similar to natural log of x. Okay, so they're good approximations to our function. And I'm going to show that soon. So that's why we care about them. It's because you can approximate your function really well with these polynomials.
It looks like you have x equals 1. We started at this exercise out with.
Yes, we are looking for the Taylor polynomial at x equals 1.
But then when you scroll down and you've actually written this out, you have x minus 1 where we had x minus a. If x equals 1, I expect you to see 1 minus a. So I'm confused.
Oh yeah. So if you remember, right, it was sigma of Cn times x minus a, right? And we're looking at the case where a is 1 here.
Okay.
I'm doing x minus 1 because a
right,
is...
so then why, so if you scroll back up, you have x equals 1.
Yes.
But A equals 1. But in the bottom,
Oh yeah, so it's
I'm
yeah.
kind of lost on that.
So so it's kind of bad notation. Yeah. Yeah, so I should, yeah, you're right. I should probably put A equals 1 here. Yeah, that's a good point.
That's how we'll see them as sort of we'll see X minus whatever this number is centered at.
Yes, that's what A
is centered at.
yes,
Okay.
A is going to be X minus whatever you're centering the power series about. Yeah. So
Okay, thank you.
yeah, I probably should write A equals 1, but I just think in the textbook and in literature, it would be X equals 1. But yeah. All right, good, good. All right, so let's do another example, okay? So we're gonna, so let's find P0, P1, P2, P3, okay, the first 3 Taylor polynomials, well, there's really 4 of them, for f of x equals e to the x, okay? And I'm going to add something to this, and a general formula for p sub k, the kth Taylor polynomial, at, so this is going to be at a equals 0. So I'll start using a, so that's a little more clear. All right, so we're centering our power series at a, so this is going to be the Maclaurin polynomials. All right. So that's what we're going to do. So remember, we're just taking the first few partial sums of the Maclaurin series. So that's not too bad. So P0, that's just going to be the function evaluated at A. That's just f of 0, which is e to the 0, which is 1. All right, so that is P0. P1, that will be f of 0 plus f prime of 0 multiplied by x. Okay, and if you just work this out, this will just be 1 plus x. Okay. P2 is f of 0 plus f prime of 0 multiplied by x plus f double prime of 0 multiplied by x squared. And this is 1 plus x squared. All right, so I hope everyone sees that f double prime and f prime of 0, those are always just going to be 1. All right, because the derivative of e to the x is always itself, and e to the 0th power is 1. Okay. And let's just do the last one, so I'll just write out the final answer. This will be 1 plus x. Oh, sorry, I made a mistake on P2. So you're supposed to divide by 2 here. Okay, so it's supposed to be f double prime of 0 divided by 2. Okay. So I hope everyone sees that. So it's going to be 1 plus x squared over 2. Okay. Sorry about that. So P3 will be 1 plus x plus 1 over 2x squared plus 1 over 6x cubed. All right. So just check this. All right. So I think we know enough information here to try and get a general formula. So more generally, so this is going to have a nice formula. So more generally, we have that the kth Taylor polynomial, this will be 1 plus x plus 1 over 2x squared plus 1 over 3 factorial x cubed plus dot 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 plus 1 over k factorial x to the k. X to the k. So that's nice. So if you just write out like a few more terms of the Taylor polynomials, this will be clear. And then if I just write this in sigma notation, this will just be sigma from n equals 0 to k of x to the nth power divided by n factorial. Okay, so we have a nice closed form for the Taylor polynomials, okay? And it's precisely this sigma that I wrote, this finite sum. So that's really nice. We're going to come back to that later. All right, let's do a few more. So next one, find a general formula for the kth Taylor polynomial at a equals 0 for f of x equals sine of x. Okay, so we're going to look at that one. Okay, so we need to figure out the first few derivatives and evaluate them at a equals 0. Okay, so first let's do that. So the 0th derivative, f of x is sine x. That's a 0th derivative, and now evaluate that at 0. So sine of 0 is 0. Okay, next, f prime of x. The derivative of sine is cosine. Evaluate that at 0, and you get 1. Okay, the second derivative. The derivative of cosine is negative sine. And evaluate that at 0, you will get 0, because sine of 0 is 0. The third derivative, so the derivative of negative sine is negative cosine. Evaluate that at 0, you will get negative 1. Okay, next, the fourth derivative. So now after 3, you usually use Roman numerals for the derivative. So I'll do f iv of x. So the fourth derivative, the derivative of negative cosine is sine. And plug in 0 into that. That is going to be sine of 0, which is 0. Okay, so we have actually landed on the thing that we started with. So let me highlight that. The fourth derivative is sine of x. And look at what we started with. F of x is sine of x. So I hope you would see that the pattern would just, it would just continue with this exact pattern, okay? So we'll just continue with this exact middle part as I keep doing this over and over. So it's going to just cycle through this whole thing, okay? So, and now the pattern repeats, all right? Because we ended up with the exact same thing we started with. So it's just going to keep cycling through this. And now the pattern repeats, all right? So this is nice. We can get a nice formula for the kth Taylor polynomial. So P sub k of x. Okay, so let me just write out the first. I'm just going to write it in its, with the derivatives. So this will be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2x squared. I'm just going to continue on the next line down because I'm running out of room. Plus f triple prime of 0 over 3 factorial, x to the third, plus f fourth derivative at 0 over 4 factorial, x to the fourth, plus the kth derivative at 0 over k factorial, x to the k. Okay. So this will come out to 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot 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 up to the kth derivative over k factorial times x to the k. I'll keep writing 5 instead of k. Okay, so why is this? Well, all of the even order derivatives, the second derivative, the fourth derivative, the sixth derivative, all the derivatives of even orders, they have 0. They evaluate to 0 at x equals 0. So that is why there are no even powers in here, okay? And this actually gives motivation as to why sine is an odd function, because look at all of the powers in its Taylor series. They're all odd powers, okay? And let me just write this in sigma notation. So this is a lot nicer when you write it in sigma notation. So this is the sum from n equals 0 to k. So there's an alternating of plus and minuses, so I deal with that with a -1 to the nth power. I have x to odd powers, so I do x to the 2n plus 1 power. And I divide by 2n plus 1 factorial. Okay. All right, so the power of x is 2n plus 1 because 2n plus 1 are all the odd numbers. Those are the odd numbers for n in the naturals. And as you see above, we only get odd powers showing up. The even powers are not there because they have 0, because the coefficients in front of them are 0. All right, so very important. So this is very fundamental. So this is our closed form for sine of x.
Sorry, would you mind explaining the 2x or the 2n plus 1, why we use it?
Yeah, so I want to encode all of these odd powers, right? I want a power of 3 to show up, a power of 5 to show up, and a power of 7, and so on, right? So if I do 2n plus 1, look at what happens if I look at the sequence 2n plus 1. Well, this comes out to when n is 0, I get 1. When n is 2, I get, wait, did I mess this up? When n is 2, I get 5. Oh, that's where I missed. Okay, when n is 1, I get 3. When n is 1, I get 3. When n is 2, I get 5. When n is 3, I get 7, and so on. These are all the odd numbers, and if you look at p sub k up here, those are exactly the powers that are appearing. I'm getting odd number powers. So how do I encode that into sigma notation? I do x to the 2n plus 1 power.
Gotcha, thank you.
Yeah. All right, so that's that. We're going to do a very similar computation for f of x equals cosine of x. All right, so this is the last one we're doing. I know this is kind of tedious and it's not that fun. So let's do this same game again for cosine of x, all right? And then we'll move on to something else. So find a general formula for the kth Maclaurin polynomial for of f of x equals cosine of x, okay? All right, so this is going to be very similar to the example with sine of x. So we just need to work out the first few derivatives and evaluate them at x equals 0. So remember, we're doing the Maclaurin polynomials, so that's when a is 0, all right?
I mean, technically, couldn't you just horizontally shift, like, you know, use the sine one, but just minus, I think, pi over 2.
Yes, yes. That does work, but it's not going to give us the same closed form that we would get now. But yeah, you're right. Cosine is just sine shifted pi over 2 units. All right, so let's just work out the first few derivatives of this guy. So the 0th derivative is the function itself. And we need to evaluate that at 0. So f of 0 is cosine of 0, which is 1. Very good. F prime of x, that's sine of x. F prime of 0 is 0.
Isn't that negative sine of x?
Yes. Thank you. Good, good. F of x is minus sine of x. Excellent. Good. So now the second derivative, f double prime of x. That will be negative cosine of x. And I'm going to evaluate that at 0. And that will give me negative 1. Good. Third derivative, that's going to be positive sine of x, okay? Because the derivative of cosine is negative sine, but there's already a negative sign there, so it makes a positive sign. And that's going to be f triple prime of 0. That will be 0. Good. And now on the fourth derivative, so f fourth derivative, you're going to see that we're going to end up back with cosine of x, okay? And that evaluated at 0 is 1. All right, so we ended up exactly with what we started with, so now a pattern will repeat. And now the pattern repeats, all right? So this is very similar to the example from before. Now the pattern repeats. All right, very good. So thus, the kth Taylor polynomial, or Maclaurin polynomial, it's going to look like this. 1 minus x squared over 2 factorial plus x the fourth over 4 factorial plus dot, 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 plus the kth derivative evaluated at 0 over k factorial times x to the k. Let me just clean that up a little bit. So it's the kth derivative. Okay. And why are there no odd powers of x showing up? Because the coefficients in front of those are going to be 0. All right, so all of the odd powered derivatives, all of the derivatives of odd order are 0. All right. So we get a nice closed form for this. This would be sigma from n equals 0 to k. And this will be, so we have an alternating of plus and minus, so we deal with that by putting a negative 1 to the kth power, x to the 2k over 2k factorial. All right, and why is it 2k? Because 2k gives us our even numbers, All right, all of the powers of x are even, so that's why I have a 2k in the exponent. All right, and this is good motivation as to why we call cosine an even function, because in its Taylor series expansion, all of the powers of cosine are even. All right, so that's kind of cool.
In the example when we used sine of x, when we did the final notation, didn't we use like negative 1 of n times, like, so does it matter? Does it matter if you use n or k as the?
Oh, it does completely matter. Yeah. So I wrote this wrong. Thank you. This should be n. Absolutely. Yeah. Thanks, Blake. So that's negative 1 to the nth power times x to the 2n over 2n factorial. Because you want the sequence that you're summing over to depend on your index of summation, which is n in this case. Yeah. All right, good. Yeah, let me fix that in my notes, actually.
How come the first term was a 1 minus, and then the rest of the signs are plus?
The rest of the signs are not plus. So I didn't write it, so that's kind of hidden in the dot, dot, dot notation, but you are going to get pluses and minuses. So, oh, are you saying I should have this as a minus sign there? Yeah.
Well, I mean, I was wondering, but also in the beginning, where it just says 1 minus x squared over 2 factorial. Like, what's the general model that you're following there?
Yeah, that's -1 because if I look at the second derivative evaluated at 0, I get a -1.
Oh, okay. And then x to the fourth, that derivative is 1, so it's plus.
Yes, exactly. And the next one will be negative and so on. Very good. Very good. Yeah, so, right, so that should be 2n, not 2k. So 2n gives us our even numbers. Good, good, good. All right, so that's that. So let me just write a quick note about these Taylor polynomials that I have alluded to before. So the nth Taylor polynomial for f of x at x equals a provides good approximations to f of x around the point. So this is why we like Taylor series, really. Around the point x equals a. Okay, and I'm going to do a nice demonstration of this right now. All right, and moreover, the approximation gets better and better. Oops. Moreover, the approximation gets more accurate, so it gets better and better. It's better and better as n gets large. Okay, as n gets large. Okay, so the 100th Taylor polynomial will be a much better approximation than, say, the first Taylor polynomial. All right. So I found a really nice demonstration of this online. So this is one advantage of teaching an online class. I can just show you guys this really easily. So let me just go to this demonstration really quick. So I have to share my browser. So I need to stop sharing here and go to my Google Chrome. So let me just do that quickly. Okay, so do you guys see this? You guys see a graph? Okay, thank you. So what I have here is the function in the red. That is the function f of x equals sine of x, okay? That's what the red is. And I'm going to now simultaneously graph the first few Taylor polynomials. And you're going to see that this purple line in the middle, it's going to look closer and closer to the graph of sine of x, okay? So look at n equals 1. That's the first Taylor polynomial. Okay, it's a decent approximation, but not that good. How about n equals 2? N equals 2, yeah, that doesn't change anything because the second coefficient is 0. So n equals 3, look at that. That looks even closer to sine of x. Okay, and just notice that the approximation is only really good at x equals 0, where we're centering our Taylor series about. All right, now let's look at the fifth one. That looks even better. All right. So if you see, as you go far away from 0, the approximation is not even close. But around x equals 0, it's a really nice approximation. All right. And as I make n get larger and larger, the approximation gets better and better. Right. So that's really what we're doing here. We're approximating our function with polynomials. And why do we like to do that? Because in computer software and real-world applications, it's easier to work with polynomials rather than these transcendental functions like sine and e and cosine. So that's really the real-world application of these things. We can approximate really nicely with polynomials. So let's look at one more function. So let me look at, how about e to the x? Okay. So let's just do e to the x. Okay, and now I don't want to center it at x equals 0. I want to make the center at 1. Okay, so our approximation will be really good around 1 here. So let me make n get bigger and bigger. So n equals 1 looks like that. Okay, that's a decent approximation. So we're approximating right here. And if I make n equals 2, oh, that's a little better. N equals 3, even better. So it's really coming to the shape of e to the x as I make n larger. All right. So, yeah. All right, and I'll just say it again. These approximations are only good around x equals 1. If you look over at x equals -4, the graphs aren't even close. All right. So these are local approximations. All right, so I thought that was cool. I found this really nice thing online, and I thought it'd kind of give some motivation for this seemingly unmotivated topic. Okay, so the next part of class, the next topic we will do is called Taylor's Theorem. Taylor's Theorem with remainder. Okay, so that's the name of the theorem. Taylor's Theorem with remainder. All right, so it's a very nice theorem. Okay. All right, so let me just talk about what what questions we're going to try and answer for the last part of class. All right, so basically we want to prove that the Taylor polynomials, the sequence of Taylor polynomials actually converge to f. Okay, we don't know that yet. We have not figured out or talked about convergence of these Taylor series. All right, so let me just write that down a little more formally. All right, so since the Taylor polynomials, p sub n, that's just a variable that we assign. Since the Taylor polynomials p sub n are the partial sums. So remember, they are just partial sums of the Taylor series, are the partial sums of the Taylor series. By definition, the Taylor series converges if what? What does it mean for an infinite series to converge? It means that the partial sums, the sequence of partial sums converge. If the sequence p sub n converges as a sequence. Okay, so we're going back to the fundamentals here. An infinite series converges if its sequence of partial sums converge. And that's what p sub n is. If p sub n converges as a sequence. All right. Good. So it will converge if the Taylor polynomials converge, but moreover, we would love if the p sub n's converge to f, the function that we're looking at the Taylor series of. So moreover, we would love or hope, we would love if p sub n of x converges to f of x. Okay, we don't know that yet. All right, so that is, let me just write this a little more formally, that is, we hope that the Taylor series for f actually converges to f, okay? That's what we want, actually converges to f of x, okay? So that's what, this is the question that we're going to be investigating for the remainder of class. All right, we want to look at when a Taylor series actually converges to the function that we're taking the Taylor series of. So far, we don't know that. Okay. All right, so that's the idea. And now we just need some terminology and some definitions. All right, so let's do it. So definition, DEF. Define the nth remainder, capital R sub n of x by, so this is just a definition. I'm going to define R sub n of x. So I'll put a colon equal sign to denote that I'm making a definition. This is nothing, this is just going to be the function itself minus the nth Taylor polynomial. Okay, so R sub n is f of x minus the nth Taylor polynomial. Okay. All right. So here's the big theorem of tonight. So theorem. So Taylor's theorem actually comes in two parts. Here's going to be part one, and then I'll do part two. So this would be theorem, part one. Part one. All right. So this is a little bit of writing, but it's not that bad. All right. So suppose f of x is n plus 1 times differentiable, okay? N plus 1 times differentiable. So that just means that its derivative, its first derivative, second derivative, all the way up to the n plus 1th derivative all exist. So suppose it's n plus 1 times differentiable on an interval which we'll call I, okay? So that's the assumption. Then, so here's the conclusion of the theorem. Then, for each x in the interval, so for each x in I, there is a number c, little c, in the interval a comma x, such that, so we get a nice formula for the nth remainder. That's what this theorem is. So that the nth remainder is this. It's the n plus 1th derivative evaluated at c divided by n plus 1 factorial multiplied by x minus a to the n plus 1. Okay. Okay, and what is a here? So I have this this interval a sub x. A is the x value our Taylor series is centered about. Okay, where a is the x value. The Taylor series. The Taylor series is centered about. Okay, is centered. Okay, so this is a very important theorem, and it gives us an explicit formula for the nth remainder. Okay, and that's very nice and convenient. So let me just write a quick note. So I'm just going to restate. I'm just going to write what I just said. This theorem gives us an explicit formula. For the nth remainder. R sub n of x. Okay. And having this explicit formula will greatly help us in determining that a Taylor series actually converges to the function we're taking the Taylor series of. All right, so we're going to see the importance of this theorem. All right, good. So now we just have the second part of Taylor's theorem. All right. So here is the part two. So theorem theorem, and this will be part 2. All right, so consider the Taylor series. Consider the Taylor series. Infinite sum from n equals 0 to infinity, nth derivative of f evaluated at a over n factorial times x minus a to the nth power. Okay, that's the form of a Taylor series, as we saw earlier in class. So it's going to be the Taylor series for the function f of x. Okay? So nothing crazy going on. I just wrote the definition of the Taylor series centered at x equals a. All right, so here is the statement of the theorem. If lim as n goes to infinity of the nth remainder equals 0. So if the limit of the nth remainder term goes to 0, then the Taylor series converges to f of x. All right, so this is a really nice theorem. Then the Taylor series converges to f of x. All right. Let's have to give someone permission to record. Just give me a second. Oh yeah, Aiden, do you have a question?
Yeah. Can we still say that it converges to f of x if f of x doesn't converge?
So f of x is not going to be a series. It's going to be a function like sine of x or e to the x, like one of those transcendental functions. So the question of whether f converges is not really a question, because f will be some nice function that is just a normal function.
Okay.
All right, so let me just talk about why this second theorem is true. So just recall, what was R sub n of x? R sub n was defined to be f of x minus p sub n of x, okay? So this is not a part of the theorem anymore, by the way. This is just my own dialogue. So recall, the nth remainder was defined to be f of x minus p sub n of x, okay? Now, what happens, so if the lim of r sub n of x is 0, then what happens? Well, look, we get that 0 is equal to f of x minus the Taylor series. Okay, and why is that? Why is that? Okay, so if the left-hand side is 0, I just put that there, right? F of x comes down as normal. F of x just comes down. And remember, the p sub n's are the partial sums of the Taylor series, okay? So by definition, p sub n converges to the Taylor series. That's what p sub n by definition converges to. All right, p sub n of x converges to the Taylor series. Okay, which would then imply that f of x is actually equal to the Taylor series. Okay, and that's what we want. So this was actually just a very short proof of part 2. So this is just a very short proof of part 2 of the theorem. All right, that's what this was. Okay, part 1 is harder to prove, so I'm not going to be doing that, but this was just a little quick proof of part 2. And I hope everyone sees that, all right? I hope everyone can see this clearly. So it suffices, so to restate everything, to show that a Taylor series converges to the function f itself, we just need to show that the remainder term converges to 0. That's what we need to show. Okay. All right, so we're going to do this now in some examples. so here's the first example. So this is, we're going to do e to the x. So find the Maclaurin. Find the Maclaurin series for f of x equals e to the x power and determine its interval of convergence. Okay, so we'll get a nice review of that and determine its interval of convergence. Okay, so that's part one of the question. Then use the previous theorem. Use the previous theorem to show the Taylor series. So I know this is a lot of writing. Use the previous theorem to show the Taylor series actually converges. So that's really what we're after. Actually converges to e to the x on its interval of convergence. On its interval of convergence. So that's really the heart of this part of the lecture. We want to prove that these Taylor series actually converge to the thing we want it to converge to. Okay, it would be kind of silly if the Taylor series converged to something else. All right, we want it to converge to f, the function. All right, so here we go. So we're gonna go through this. So first of all, by a previous example, so we did this in the beginning of class, we already have a closed form for the Taylor series of e to the x. By a previous example, or Maclaurin series, we know that e to the x has Taylor series the following. All right, this is from previously in class. We got an explicit formula for the kth Taylor polynomials, and I'm just going to be using that. It has this as a Taylor series. Okay, it's x to the n over n factorial. Okay. So just look up in your notes. We figured this out in the first half of class. Okay, and we want to show that this series actually converges to e to the x. Okay, we don't know that yet. All right, so we're going to do this step by step. So first let's find interval of convergence. Okay, first let's find interval of convergence. So that's step one. Alrighty. So this will be a nice review of last class. So what do we do usually? We use the ratio test. Use the ratio test. Use the ratio test. All right. So for the ratio test, we need to set up this limit capital L. All right. So I hope this will be familiar from last time. We set up this capital limit L. It's the lim as n goes to infinity, absolute value. Okay. N plus 1th term divided by the nth term, okay? So that is as follows. It's x to the n plus 1 over n plus 1 factorial. I'm dividing by a fraction, so let me just multiply by the reciprocal. Multiply by the reciprocal of the nth term, n factorial over x to the n. All right, so I hope that's okay. This is just the n plus 1th term divided by the nth term, but I'm multiplying by the reciprocal since we're dividing fractions. All right, done. So next, we actually did this last class, so you pull out the absolute value of x, and this is a lim as n goes to infinity of 1 over n plus 1. Okay, so use that property of factorials. You break that up into n plus 1 times n factorial. The n factorials cancel out. Excellent. This is 0. This is 0. And now we set this to be less than 1. Okay. And this, and This inequality is true. So we actually did this last class. This inequality is true for all x in the real numbers. So our interval of convergence is minus infinity to infinity. All right, is our interval of convergence. Good. So we got that sorted out. So good, at least we know that our Taylor series actually converges everywhere on the real line, okay? So it converges, we just don't know what it converges to. But we will now show that it actually converges to e to the x, okay? It actually converges to the correct thing. All right, next. So now we show this series, x to the n over n factorial, converges to e to the x, okay? And we do this by showing that remainder term is 0, okay? So that was theorem part 2. We do this by showing lim as n goes to infinity of r sub n of x is 0, okay? Then the result follows by theorem part 2. Then the result follows. So I'm just being very explicit right now. On the next example, I'll move a little faster. Then the result follows by theorem part 2, okay? Theorem part 2 said if the limit of the remainder term is 0, then good things happen. Our Taylor series actually converges to f of x, okay? So that's what we set out to do. So this is what we're doing. Very good. All right, so let's compute this guy. Do we need that? No. Okay, so we look at lim as n goes to infinity. So we're actually going to look at the absolute value of the nth remainder term, okay? All right, and so this is equal to lim as n goes to infinity. So now we actually use that explicit formula for the nth remainder. That was theorem part 1. So we have that the nth remainder term is actually equal to the n plus 1th derivative evaluated at c divided by n plus 1 factorial multiplied by x to the n plus 1. Okay, for some c in the interval a comma x, all right? This is by theorem part 1. So this is the, this is by theorem. So remember, theorem part 1 gave us that nice explicit formula for the nth remainder. This is by theorem part 1, okay? Very good. And now we're in good shape because the n plus 1th derivative of e to the x is always e to the x, all right? And then I just plug in c. So this is nothing other than e to the c over n plus 1 factorial multiplied by x to the n plus 1. Okay, so I'm just moving the absolute value to that x, to the x term, because everything else is positive. Very good. So I hope everyone's okay with why the numerator turned into e to the c. The derivative, the n plus 1th derivative of e to the x is just e to the x, and then I just plug in x equals c. All right, good. We want to show now that this is 0. So I need to say something now. So now, since the series x to the n over n factorial converges for all x absolutely by the ratio test. So that was by ratio test. That's what we figured out before. Okay. By the divergence test. By the divergence test, we know that the limit of its sequence terms goes to 0. So that was the contrapositive of the divergence test. So since this converges for all x absolutely by the divergence test, lim as n goes to infinity of x to the n plus 1 power over n plus 1 factorial, that's 0. So important step, I'm taking the contrapositive of the divergence test and applying it, okay? Since it converges, I know that its sequence terms goes to 0. Yeah, so we're done actually. So by that note, this last thing on the equal sign, this is 0. So let me just copy it down. Okay, so we know that this thing is exactly, well, it's actually e to the c times 0, which is 0. And we're done. So thus, lim of the absolute value of r sub n of x is 0, which implies that lim of r sub n of x without the absolute value is 0. And we're done, which implies the Taylor series converges to e to the x. As the Taylor series converges, to e to the x. There we go. So we see that that explicit formula for the nth remainder was really important, okay? Cool. So if anyone has questions, just let me know. So let's do the same thing.
Daddy, can I have a napkin?
I think someone's mic is on. Just
Oh shoot, mine is, sorry.
it's okay. Okay, next example, we're going to do the same exact thing for sine of x, okay? Do the same thing for f of x equals sine of x, okay? All right, so by a previous example, we already have the closed form for the Taylor series for sine of x. So by a previous example, the Maclaurin, so remember Maclaurin series is just a Taylor series centered at x equals 0. The Maclaurin series for sine of x is, so this was by previously in class, so it was -1 to the nth power multiplied by x to the 2n plus 1 over 2n plus 1 factorial. Okay? So that was just from earlier. So first let's find the interval of convergence. So first let's find interval of convergence. Okay, so use the ratio test just like before. All right, so for the ratio test, we need to look at this limit capital L. Lim as n goes to infinity, it's the n plus 1th term, so absolute value. The n plus 1th term, so it's x to the 2, done. It's x, so what does that come out to? Yeah, so it's x to the 2n plus 3 over 2n plus 3 factorial. Okay, so I get that if I plug in n plus 1 for n. All right, so I hope everyone's okay with that. So if I plug n plus 1 here, I get 2n plus 3. Okay, And then let me multiply by the reciprocal. That's going to be 2n plus 1 factorial over x to the 2n plus 1. Okay? Very good. And if you just do some simplifications, this will be lim as n goes to infinity. You're going to have an x squared. Actually, I can bring the x squared outside of the limit. So let me just do that. So you're just going to do some algebraic simplification. So you get absolute value of x squared multiplied by the limit of 1 over 2n plus 3 times 2n plus 2. Okay? And I'm just using that property of factorials down here. Good, and I hope you guys agree that this limit is 0. I have 1 over infinity. And this will always be less than 1. This is less than 1 for all x in the real numbers. All right, so technically this less than 1 I'm setting. Remember, I have to set it to be less than 1 and see which x values solve that inequality. But it's clear that every x value will solve this. Okay, and that just means that our interval of convergence is minus infinity to infinity. Excuse me. Thus, the interval of convergence is minus infinity to infinity. So this series will converge no matter which x value we plug into it. Now we just need to make sure that it converges to the right thing. Does it actually converge to sine of x? All right. So next, we show that lim, so we want to show that the remainder term goes to 0. Okay, and just recall by theorem part 2, that will prove that the Taylor series converges to the correct thing, that it does converge to sine of x. Okay. All right. So first of all, let me just pick an arbitrary real number. So let x be a real number. Okay. Then by theorem part 1, which was the explicit formula for the remainder term, by theorem part 1, the nth remainder of x will equal f n plus 1th derivative evaluated at c divided by n plus 1 factorial times x to the n plus 1 for some real number c. Okay, so this was that very powerful theorem, part 1. It gave us an explicit formula for the remainder term, okay? Good, so let's just look at the numerator, by the way. It's going to be the n plus 1th derivative of sine of x. Okay, so let's look at the absolute value of that. So since the absolute value of n plus 1, the n plus 1th derivative of x, this is going to be one of two things. This will equal the absolute value of cosine or the absolute value of sine. And why is that? Because I'm looking at the n plus 1th derivative of the function sine of x and the derivatives of that cycle between sine and cosine. And the absolute value gets rid of the negative sign that appears, okay? Thus, both cosine and sine are bounded by 1. Okay, that's what I'm trying to get at here. This implies that the n plus 1th derivative of f evaluated at x, actually evaluated at c, let's use that. Evaluated at c is less than or equal to 1. Very important. Okay, so I've put this on some homeworks as hints. Cosine and sine are bounded in absolute value by 1. All right, so that's why that thing in the numerator is less than or equal to 1. All right, so here we go. So now let's look at the lim of the nth remainder term, the absolute value of the nth remainder term. So lim of the absolute value of r sub n of x, this will be less than or equal to x to the limit x to the n plus 1 over n plus 1 factorial. Okay, and I'm using this estimate here. I'm using this inequality. The numerator is less than 1. That's why the f to the n plus 1 has disappeared. And it's just x to the n plus 1 there. Very good. And this limit by the divergence test is 0. Just like the previous example. This is 0 by the divergence test. All right, and we're in good shape. So we're done, actually, by the divergence test. So we just figured out. So we actually figured out that the limit is less than or equal to 0, not that it is 0. But there's a theorem called the squeeze theorem, which I'm not going to go into, that will imply that the limit of the less than thing is 0. All right. So I'll just write that just to be really rigorous. So by the squeeze theorem, if you would like to look at that, that is in our textbook, by the squeeze theorem. Lim, as n goes to infinity, of the absolute value of x is 0. Okay. So the reason why I'm writing that is because our limit is actually less than 0. That's why I need to write the squeeze theorem thing. All right, and now since the limit of the absolute value is 0, then the limit without the absolute value must be 0. Okay, so we're done. So by theorem part 2, by theorem part 2, the Taylor series, the Taylor series converges to sine of x. All right, so everything is converging to what we want it to. Okay. All right, and if you don't know what I said about the squeeze theorem, do not worry about it. I'm not gonna do anything on that on homework or the exam, but it's something interesting if you want to look at it. Okay. Okay, so we're just going to do 2 very quick examples of computing Taylor series, and we're going to be done. All right, so the first example, find the Maclaurin series for cosine of the square root of x. Okay. All right, so this is not hard at all. Okay, so recall cosine of x has the following Taylor series. So cosine of x is equal to this as a Taylor series. So this is from earlier in class. It's -1 to the n multiplied by x to the 2n over 2n factorial. Okay, so that's from earlier in class. Now all I need to do is wherever I see an x, I plug in a square root of x. Okay, thus. So this is going to be on the homework and the finals, just simple computations like this. So thus, cosine of square root of x. So all I'm going to do is wherever I see an x, I will put a square root of x. So this will be x to the 1/2 to the 2n power. Okay, so does everyone see what's going on? I'm replacing this x with x to the 1/2. That's it. That's all you need to do. And now just use properties of exponents to clean this up a little bit if you wish. This will be infinite sum at -1 to the n. So multiply the 2 powers together, you just get x to the n over 2n factorial. That's it. That's all you need to do. So these are the kinds of questions you'll see on the final for Taylor series, okay? And you won't have to memorize any Taylor series, of course. All right, let's do one more, and then we will call it an evening. Yeah. So let's find the Maclaurin series. Find the Maclaurin series for sine of x squared. Okay. So sine of x squared. Okay. So recall that sine of x had the following Taylor series expansion. So this was from earlier in class. Sine of x has this Taylor series. -1 to the n multiplied by x to the 2n plus 1 over 2n plus 1 factorial. That's directly from previously in class. Now, all you need to do is wherever you see an x in the series, you plug in x squared. That's it. So let me do that. So this would be -1 to the n. So it's going to be x squared to the 2n plus 1 power over 2n plus 1 factorial. Okay. Very good. And now let's just use properties of exponents to clean up this last term here. Okay. And that's about it. So before I go, just someone asked a question about material on the midterm, on the finals. I'll answer that quickly. So first of all, let me just multiply these exponents together. That will be x to the 4n plus 2. Yes, I hope that's right. X to the 4n plus 2 over 2n plus 1 factorial. All right, so that's that. And these are the kinds of questions you would expect on the final, okay, and on the homework for the next homework, all right?